In this video, I will explain ridge regression and then run through a quick coding example in our studio. Regularization refers to a set of techniques used to prevent overfitting in statistical models by adding a penalty term to control the complexity of the model and improve its generalized performance on unseen data. In predictive modeling, we often want to find the optimal complexity in our model to minimize error, and this can be achieved by finding the balance between underfitting, which is known as bias, and overfitting, which is known as variance. This graph on the right is referred to as the bias-variance trade-off. One technique for reducing complexity is stepwise regression, but this is simply removing independent variables from the equation to reduce complexity. We may want to keep highly correlated independent variables to understand their effects. For example, in marketing, we often find our media spending in different channels are highly correlated, but we want to determine their independent effects. In addition to producing more accurate models, ridge regression tends to produce more stable coefficient estimates compared to ordinary least squares regression. This is especially true when dealing with datasets with a large number of predictors or when the predictors are highly correlated. Therefore, stability of coefficient estimates is also a factor. To prevent overfitting, we may want to water down the model to reduce the coefficients. When we have highly correlated variables, our coefficients can become unstable. As you might imagine, this also happens with polynomial variables where estimates can vary greatly. In the example graph, we are seeing the relationship with a car's horsepower and the size of the engine. But imagine that our test and train split produced a poor fit on our test data. But if we change the slope for our regression equation, we could get a better overall fit with both our train and test data. In ordinary least squares, we decompose the variance into the explained and unexplained. The explained is what is driven by the model, and the unexplained is our error. Our ordinary least squares regression minimizes our error, and we can use this decomposition of variance to calculate our R-square. The way ridge regression reduces overfitting is by introducing a penalty term. So, we are still using our concept of minimizing our error, or sum of squared residuals, but we are adding to this a penalty of our slope squared times lambda. So, by lowering our slope or coefficient, we are reducing the penalty, and conversely, if we have high slopes or coefficients, we have a higher penalty. We are going to be referring to this penalty multiplier as lambda, but in some of the literature, it is referred to as alpha. We are going to look at ridge regression in R, which reserves alpha for the type of regularization, meaning ridge, lasso, or elastic net. Lasso not only shrinks the coefficients, but can also perform variable selection by setting some coefficients exactly to 0, which you may not want to do. Ridge regression is guided by a minimization function. It's a formula, and as we increase lambda, our minimization, or loss function, lowers our slope at the cost of increasing our error in the training data. This creates a tug-of-war between our minimizing our error and our minimizing our penalty. So, what's a good value for lambda? Or to say another way, can we optimize lambda? The answer is yes. Our data is randomly divided into k roughly equal size subsets or folds. Then, we are going to come up with a range of lambdas, and then the model is trained and tested on each fold. This is a looping over the range of lambdas and folds to get the test errors. The average validation error across all folds is computed. As you can imagine, the lambda value that minimizes the average validation error is selected as the optimal lambda. However, maybe we want a simpler model to further reduce our complexity. For this, we could follow the one standard error of the minimum lambda rule. Here is a plot of the lambdas and errors, just described as looping over a range of lambdas and k-fold test sets. The y-axis is our output metric. The x-axis is our value of lambda. This is usually represented as the log of lambda. We use a log because the lambda can grow rapidly. If we go from lambda of 4 to 8 to 16 to 32 and then to 64, the scale could get confusing. A log interpretation would make this progression linear instead of exponential. Finally, the vertical line lambda .min with the red arrow represents the best lambda for minimum error. The lambda .1se with the green arrow represents our one standard error or one standard deviation rule, which represent a simpler model which does not substantially sacrifice accuracy. Now let's hop over to our studio and look at ridge regression from a coding perspective. T-cars dataset, which comes preloaded in our studio. To explore this, we can type help mtcars into the console. In the output pane in the lower right, you will see information about this MTCars dataset. This will give you a description along with variable names and labels. The first thing we will do is pull in the libraries for our analysis. The library glmnet is used for ridge regression. The install packages has already been run. First, we will identify our response variable as horsepower with the variable name HP and assign it to Y. Next, we will select our predictor variables and assign them to X. As you can see from the output window in the lower right corner, MPG is miles per gallon, WT is vehicle weight, QSEC is time in the quarter mile, and DISP is displacement or engine size. I will be showing how the coefficients for these variables change over different levels of lambda. I would like to point out that I am using these variables in their raw format. For sake of simplicity, I will not be standardizing the independent or predictor variables. Standardization puts the variables on the same scale and helps in determining relative impact, but this is outside the scope of this very simple example. Next, we can run the correlation matrix and show the relationship between our predictors. This correlation matrix will appear in the console window below. These variables make sense. Higher MPG is negatively associated with both vehicle weight, represented by WT, and engine size, represented by DISP. We can note that higher the QSEC, the slower the vehicle. Since QSEC is time in the quarter mile, the larger the number means the longer it takes to finish the quarter mile. This translates to slower vehicles getting better gas mileage. Let's run a simple linear regression and call it standard model. We will use the values in the below column estimates to compare to our ridge regression. Again, our response variable Y is horsepower, and the estimates are the coefficients or slopes. For example, for every 1 unit increase in MPG, horsepower decreases by 2.69 units. Now let's separately run our ridge regression. We will assign the name model to our ridge regression, and we will name our k-fold cross-validation CV model. From our CV model, we can identify our minimum lambda and name it best lambda, and our one standard error from our minimum lambda as lambda_1SE. We see that the lambda value for best lambda is 13.5, and for our lambda_1SE, we have a value of 104.8. Next, we will plot out how our mean squared error increases as we increase lambda. As previously mentioned, we take the log of lambda for comparison purposes. Now let's expand our plot. The first vertical bar is our minimum lambda and appears to be at the log lambda value of 2.5. The second vertical bar is our lambda_1SE and has a log lambda value of about 4.5. Finally, we will explore how these different lambda values impact our coefficients. Let's expand. Each of our 4 predictors is plotted, and we can draw a line for log lambda of 2.5. My apologies, that should be a straight line. In the same way, we can take our log lambda value of 4.5 for lambda_1SE and draw a line. Now I will create a small data frame to compare these coefficients for 3 models. The first column is our simple linear regression named LM_coef. The second column is our coef_best representing our minimum lambda, and our third column represents the lambda_1SE. On the far left of the graph, we have our coefficients corresponding to lambda equals 0, which is our simple linear regression. These are numbered 1 through 4. At the top we see number 2, next to the beginning of the red line. The number 2 represents the weight variable listed as XWT, which is the second in our list of LM_coef column. The value for XWT here is 9.2. Continuing to focus on our weight variable, we see that the minimum lambda for XWT is 9.86, which crosses the x-axis at about 2.5. As we move farther along the x-axis to a log lambda value of about 4.5, we get a slight drop in the coefficient to 8.8. The green line at the bottom with the number 4 represents the QSEC, or seconds for the quarter mile. At lambda equals 0, the linear regression coefficient is negative 18. At log lambda of 2.5, we have the minimum lambda, and our coefficient is negative 15. And at log lambda of 4.5, we have a coefficient of negative 8. Well, my YouTube friends, I will save further potential exploration of ridge regression for future videos. This is my very first video in the analytics space, so I am actively soliciting feedback. Please leave a comment, or a like, or even a dislike. I value your time. Thanks for watching.